Welcome everyone. Thanks for attending. Thanks for your time. So I would like to give you a quick run through why electrification matters those days, and give you then in a minute 3 reasons why you should consider this also for your vessels. Now, welcome to the decade of decarbonization. Fuel efficiency has been around for the last 10 years. So we enter into a new kind of decade where the reduction of greenhouse gas emission will hit shipping in a much bigger scope than it has in the last 10 years. There's mainly 2 additional drivers which we haven't had before. One, of course, on the legislation side, there is, of course, the introduction of the EEXI, and of course the next stage of EEDI. And on the horizon, there will be some kind of cost for carbon, right? Be it a carbon tax, be it carbon credits in a trading scheme or whatever. But carbon or greenhouse gas emission will cost in addition to what it does today. There are also new market drivers we are seeing, which is limiting or improving access to capital for those who are exceeding current standards, which is the so-called Poseidon principles, but also the loans which are linked to environmental, society, and government's principles. And of course, there is some business risk which will increase if your vessels fall into a bad category on this new carbon intensity index, here abbreviated with CII, right? Which will have an impact on day rates and time charters quite soon. Whenever this carbon intensity index is now approved by this week's MEPC session. Well, what you need to do from our perspective, there's now time for a fleet strategy, how you make your vessels fit for the next decade, right? Especially your existing fleet fit for the next decade. 2023, there's EEXI coming, and you want to be clear to comply with EEXI, that you take investments that also give you improvements in your carbon intensity index, which is then the indicator running over it. Many of you know that EEXI is just a threshold you need to jump over. But of course, the decisions, the way you do this very much is quite critical, that you really can extend the lifetime of your existing fleet and don't have to scrap vessels which are still very young. And of course, there's also the opportunity now and a good chance to rethink future new builds, to make them future-proof, to really comply above 2030, obviously, to comply with a much less footprint of greenhouse gas emissions. All right, if you look at technical solutions to get your greenhouse gas emissions down, I mean, there are 3 areas we look at. Of course, it's all about engine optimization and fuel flexibility, which we not touch today. Then, of course, it's everything around the propulsion itself, so energy-saving devices, propulsion improvement devices, and what have you. And the 3rd area in the middle here, which we would like to focus on, is electrification. And if we talk about electrification, we talk about a wide range of variations, starting from a simple shaft generator to, of course, hybrid vessels, shore connection, diesel electric, different propulsion concepts, which you will see later. So now I would like to give you 3 reasons now why electrification is relevant and how it will help you improving your greenhouse gas emission footprint. Reason number 1, whenever a vessel can connect to shore and can take power from the grid, it will immediately profit in many areas of the world that the grid, the power in the grid is already green in a quite big percentage. In many areas of Europe, it is around 50%. So basically, for your shore power, you reduce your carbon footprint immediately when you get connected 50%, right? Of course, if you then think about new vessel concepts, which we'll show you later, short distance hybrid vessels or full electric vessels like tugs and ferries, they will of course then be charged from the grid, and they will immediately halve their carbon footprint, taking power from the grid. Now, what you need to consider now, if you look at new vessels, that you consider this in your new build design right away, that you reduce retrofit costs for shore power capability in the years to come. Second reason, an electric propulsion system, and of course many people know it from the car industry, is of course, if you take starting point 100% renewable energy as a starting point, it is the most effective and efficient propulsion system, right? So they are above, a little bit above 10% losses if you do a full electric propulsion system. That of course is limited at the moment in range. So you only have vessels with a certain range profile that can do this. But every vessel that will stay in that range profile, so short sea tugs, double-ended ferries, inland waterway vessels, etc., they will be full electric. So everything that can go electric will be full electric, just for the simple reason that the losses in the combustion process or in the propulsion train are so little in a full electric system. Reason number 3, if you look at new vessels and different propulsion designs and propulsion train designs and setups, of course, the current standard of designing a vessel is around the operational profile of the vessel, right? Now the question is whether the next years will not get, and that's my prediction, we will get to another speed reduction in shipping, right? Because many vessels are without speed reduction not able to reach their EEXI targets of the existing fleet. And of course, we have a lot of uncertainty about future alternative power sources. So keyword is fuel cells, or of course, much cheaper batteries from maritime use, etc. So there will be different power sources. And now, what electrification will give you, and that is basically the core of the next chapter, but Tony runs you through, is looking for alternative, much more flexible propulsion concepts for your new build vessels. What this will entail, these new propulsion concepts, it will shift from what we see here from a today very engine-centric setup of your vessel towards a software-centric setup of your vessel. And the part in the center of a more flexible state-of-the-art propulsion system is the so-called energy management system, which is a new software category on vessels, which is performance focused, which is basically optimizing the interaction of different power sources and different power consumers. And of course, it comes on top of the already existing power management system, which of course is a system that is safety related to avoid blackouts, to turn on and off aux engines at the moment.
Okay, so now we're going to talk a little bit more technical than before. I'll take you through a number of different vessel types where we've already installed or are in the process of installing electrical solutions to increase our flexibility and, of course, to reduce emissions. And I first want to talk you through a system we have on a small 5,000 deadweight ton bulk carrier. On this kind of vessel, the traditional solution is a two-stroke engine with FPP with fixed pitch propeller. We studied a number of different solutions for this type of vessel. We looked at two-stroke with the shaft generator, or PTO/PTI. We looked at four-stroke with shaft generator, four-stroke hybrid with shaft generator, and of course we looked at FPP versus CPP, fixed pitch propeller, against controllable pitch propeller. And we ended up with a solution with a four-stroke with hybrid PTO/PTI system. I'll talk you slowly through this diagram on the top right, so you understand a little bit what we have here. Okay, let's start with the propeller, because that's what we're trying to do. We're trying to move some water if we can, or the vessel. So we have here a controllable pitch propeller rated at 2.4 megawatts. This is connected, of course, to a gearbox, also rated 2.4 megawatts, and with twin input to that gearbox. One input is a 1.6 megawatt engine running on diesel. The other input is a 800 kilowatt shaft generator machine, which is then connected to a converter system here, as you can see. Also connected to this converter is an energy storage system, so a battery pack of 1 megawatt hour, and a 300 kilowatt tunnel thruster, so the bow thruster is connected to this converter, and we have a connection to the shore connection going directly to this converter, for reasons we'll come on to in a little bit. What's not shown on this drawing for ease of understanding right now is a connection from this converter to the ship's main switchboard, which you could imagine here, and also connected to the switchboard the auxiliary engines. Okay, so this system's got a number of different modes, which again I'll try to talk you through slowly here. Some of you may be familiar with shaft generators in PTO, PTI mode. Excuse me. But very briefly, we have a PTO mode, power take off mode, where you're taking power off this machine here. Power is going back to the converter, being converted from variable voltage, variable frequency to constant voltage, constant frequency, and exported to the ship's network. Of course, this is when the engine here is running, driving this machine and driving the propeller. The propeller speed, of course, power has to below the engine rating to make this happen. Why do we do this? Well, if we do that, we can increase the loading on this engine and make it run at better efficiency. And if we're exporting power back to the main switchboard, we can maybe turn off some of the auxiliary engines on the main switchboard and save fuel that way. Then we have PTI mode, or power take in mode, where power is going the other way from this converter to this machine, now operating as a motor, which is driving the shaft. This can either be in parallel with the main engine in boost, so when you need to go higher than the engine rated power, you use this machine to drive the propeller higher, or it can be with the engine declutched and running solely on this machine. In this mode, the power for the propeller comes from either the auxiliary engines or from the battery pack. And of course, when you're running this, there's a motor with power just from the battery pack, you are completely green, you're 100% no emissions. So in this mode, you can have zero emissions maneuvering going into and out of port, for example. So it gives you good savings that way. Additionally, we have peak shaving mode. Now, peak shaving mode is a way to provide the transient load to the propeller from the battery pack and not from the main engine. Okay, why do we do this? We want to have a constant load on the main engine. That gives you the best fuel usage. If you're constantly increasing and decreasing the power of the engine, the fuel usage is not so good. So the transient load as the propeller power changes as you go through the swell comes from the energy storage system. So again, peak shaving is to give you constant load on the engines and to give you better efficiency of the engine. Additionally, you can see we have a tunnel thruster driven from this system. This is because we have a converter anyway, so let's use the same converter to drive the tunnel thruster. But then this gives us a possibility to get the power for this tunnel thruster either from the main engine or the auxiliary engine or from the battery pack again. And finally, we have a shore connection coming into here. Why do we do that, you may ask? Well, this vessel goes into ports which have got either 50 or 60 hertz on the shore supply, and the vessel wants 60 hertz. So when we're connected up at a 50 hertz port, we connect it into this converter, and we convert that from 50 hertz to 60 hertz and export it to the main switchboard. Okay, you can see already we've got lots of flexibility design in the system. There is more besides that. Of course, we could add more power sources to the ship's network. That's one option. We can also look at modifying the fuel for the main engine. And the benefit then of having the battery pack using peak shaving is that you can then overcome any degradation in engine power take-up with the battery pack. Well, for future fuels, at the moment, we don't know how well they will take on load. The engines will take on load. So having a battery pack in parallel is a good belt and braces in case performance isn't good enough. Okay, so that's a brief run through that. Brief, maybe not so brief. So what's the result of all this for this vessel? As you can see in the bottom left there, we have some figures there. The installed power is reduced by 10% compared to the two-stroke case with auxiliary engines. Running hours for engines reduced by 12%. Fuel consumption is reduced by 15%, and CO2 reduction by 20%. So significant savings there with this system, and significant possibilities for future flexibility. Okay, let's move on. And of course, this concept is scalable. Here we have a general purpose cargo vessel, again with a very similar solution, as you can see. Again, the base case will be a two-stroke with FPP, fixed pitch propeller. But again, we have a four-stroke hybrid PTO-PTI system in place. Here, in this case, for the main engine, we have, I think it's a 6 megawatt main engine and a 2.5 megawatt shaft generator. So, for bigger vessel, the concept is totally scalable. You can see also here, similar system here. On this version, we have got the ship's main switchboards shown and the auxiliary engines. You can see perhaps now why I didn't show it on the first slide. You can see we have additional tunnel thrusters. You can see also we have a shore connection, in this case going direct into the main switchboard because there's no requirement to go into a 50 Hertz port. And you can see we have an additional tunnel thruster or thruster off the separate switchboard because this has got a basic DP functionality on this vessel. But most of the thrusters, two of the thrusters, are run from the converter. So for this, the same operational modes apply as we saw for the bulker, and similar savings are achieved. Just to show you the scalability. If we build on that concept a bit further, maybe we switch segments into the VOPAX. Maybe, of course, we're switching into the VOPAX segment. Here we have a VOPAX vessel. Traditional base case we've taken as base case is a 4x4 stroke with CPPs. So controllable pitch propeller, twin connected to a gearbox, twin inputs from two engines on each gearbox. But we've replaced this with a 4-stroke hybrid PTO-PTI system similar to before, but because it's twin skeg, we have two of them. Okay. Again, we have similar operational modes for this vessel. You can see, so I forgot to mention that for the battery pack, we have 2 by 2.5 megawatt hour for the battery pack. So significant battery packs for this to also allow you some running on batteries and some peak shaving. So again, for this kind of system, we can see we have some significant savings. We have installed power reduction of 16%, running hours by 20%, CO2 7% down, NOx reduction of 13%, and OPEX saving of 8%. So going to an electrical system here then gives you better savings, and again gives you future scope to add more flexibility for the future. So I've talked a lot about diesel mechanical. So diesel mechanical as a diesel directly connected to a propeller so far, but that's not always the answer. We already know it that for vessels which operate more at variable speeds, have not sailing across the ocean at constant speed, the diesel electric is already a well-known and well-used solution. But for this 60-car passenger ferry, we've compared a diesel electric with a 4-stroke diesel electric hybrid system. For this, each propeller here is 8 megawatts, driven directly from an electrical motor. Each of those is fed from a converter, and of course the converter is fed from the switchboard with I think 2 by 6 megawatts and 2 by 5 megawatt engines attached to it. And there's some tunnel thrusters also at 1.1 megawatts. You can see some energy storage systems also here. These are 1.5 megawatt hours. And for this system, we have some slightly different modes possible now, because we're now looking at diesel electric hybrid system. But we still have, of course, peak shaving, so the transient load on the system, both from the propeller now and from the hotel load, can be taken up by the batteries. But we can also use these battery packs as main source of power. What does that mean? That means we can run, say, for example, with 2 engines plus a battery pack, providing the main power. And then when the battery pack is discharged down to its minimum level, you turn on extra engine, use that to drive the propulsion, and also to charge the batteries at the same time. And that is the batteries operating it as a main source of power, as a separate classification mode. So that's possible then, so that gives you further savings on use of engines for that system. And then, of course, we can use the batteries for green mode import, and even more so if you have shore power connected to that. So when we're comparing that, the hybrid system, even with a pure diesel electric, you've got significant savings on engine running hours of 20%, CO2 reduction of 3%, consumption savings of 3%, and OPEX saving of 5%. Difference between OPEX savings and consumption savings. In OPEX, we're including things like maintenance hours, etc., etc. Okay. Moving on a little bit, as Torsten mentioned earlier, the best grid to wake efficiency is if you can go full electric. Now, for vessels which are large powers or going long distances, at the moment, full electric is not viable. We haven't got the energy density in the batteries yet to be able to do that. I'm sure we've got some battery suppliers online who will tell us it's coming soon. Let's see what happens. But already for fully electric ferries, small fully electric ferries, full electric is viable. You can see here two small vessels. They are double-ended ferries. They have a thruster fore and aft. I think the thrusters are about 600 kilowatts. And attached to that is a converter and 2 by 300 kilowatt hour battery packs. The most important thing for this vessel, apart from the batteries, of course, is the shore connection. So when the vessels are in dock for 10-15 minutes, offloading and loading the cars, you need a quick connection to the shore supply, charge the batteries from that shore supply, and then sail off again to the other dock. Of course, you need power on the shore to come from somewhere, and some of these remote fjords, that's also a challenge, but that's another story. But we have that possibility. Also, you can see here there's 2 high-speed engines attached to those converters. These are not for normal use, they're for emergency use. So under normal operations, they are not running. I've not shown you any comparison figures there for fully electric versus something else, because the answer is either infinity or 0, depending on how you calculate it, because these are fully emission-free. Okay, and finally, I said I had 6. We have something completely different, as someone once said. And this one is a shuttle tanker, which probably deserves its own webinar all to itself, but I'll try to give you the 2-minute version of this. Traditionally here for a shuttle tanker, you would have 2 two-stroke engines, each driving a fixed propeller, and a totally separate auxiliary system. But we've got something rather different here. We have got a 4-stroke DFDE, so dual fuel diesel electric hybrid with CPP, with controllable pitch propeller. Lots of bells and whistles. And you can see here, basically it's diesel electric. So you have a shaft, 2 propulsion motors fed from a converter with a battery pack and engines. Engines are dual fuel. You can see on the left some quite remarkable figures claimed for NOx and SOx reductions. Unfortunately for us, we can't claim that's thanks to the electrification. That's in fact due to the engines burning a mixture of LNG and VOC, so the volatile organic compounds which evaporate in the cargo tanks, and burning that combination is what reduces the NOx and SOx. But the CO2 reduction and everything else, and changing from a two-stroke to a diesel electric system is what gives you significant savings going forwards. So compared to the two-stroke solution, we have machinery power reduced by 10%. We have running hours reduced by 29%, which is quite remarkable. Overall fuel reduction of 10%. And then, of course, we use the battery packs, which in this case are quite small, I think 2 by 250 kilowatt hour. They're used just for peak shaving for this vessel. Already, this is excuse me. Already, this is very flexible, but you can see we could also add future new power sources, and we can configure for alternative fuels if we decide to replace the LNG one day. We have the battery packs to do peak shaving and take up any transient loads required. So maybe that's a very quick talk through that vessel. I said I had 6 examples of what we've done so far, and I have, but here's one we're doing at the moment, and it's not a project in operation right now or contracted right now. But the question was about fuel cells earlier, and we have a project here where, for a cruise vessel, where we're currently looking at adding fuel cells. On this vessel, we've already supplied the engines, the electrical system, and the propellers, and now we're being asked to add 2 by 2 megawatt fuel cells and 1.6 megawatt hour battery. Why batteries and fuel cells together, you might ask? Well, fuel cells are very good at providing constant load, but they're not so good at taking up transients. So the battery is there again to take up the transients. You can see, at least conceptually, it's quite easy, or electrically also, to plug these into the existing switchboard and not make a great big difference to the system. Of course, they have to find the space for these on the vessel, and that's the challenge for fewer passengers or fewer crew for this cruise vessel. But at least electrically, if you have the switchboards, you have the flexibility there to add things into it. So we've looked at some of the case examples of what's the strategy for finding the best solution now. Okay, now don't worry, I'm not going to talk you through this slide and talk about EEXI in 2030 and 2050. Let's not go there. But what's the best way forward? For us, the best way is for a partnership of owners, designers, and suppliers to study a vessel and find the best solution. The solution is going to depend very much on whether we're looking at retrofitting existing vessel, or we're deciding, okay, no point in retrofitting, let's go new build and start again. The solution will depend also very much on the operational profile for the vessel, and we'll come on a little bit to that in a couple of slides' time. And the solution will depend a lot on the owner priorities. We already see different owners doing different things. Some looking at methane as a fuel, some ammonia, some hydrogen, some fuel cells with batteries. And it's far from certain which technology is going to win out in the future. In fact, if one wins out, or we end up with a combination of those technologies for the future. Our crystal ball isn't good enough yet. But what we do know is we need the flexibility. And electrical systems give us that flexibility now. So we have the flexibility of electrical systems to add future power sources. If we're doing something new now, make sure we have sections or spare sections in the switchboard, or space for spare sections in the ship's switchboard, so those can be added more simply in the future. If we're looking for hybrid, or looking for hybrid in the future, at least think about where we're going to put the batteries in 10 years' time when we design vessels now, because doing it later is more tricky. And of course, shore power is going to become mandatory soon, so think about how we're going to get the shore power onto the vessel at this stage, rather than when we're in the yard trying to make it happen. As Torsten said, electrification on its own is not the answer to get us to 2050, but we see it as one of the 3 pillars. The 3 pillars, as we mentioned, were alternative fuels, energy-saving devices, and electrification. But it's important that we look at the electrical side now, to give us the flexibility to cope with what comes in the next 10, 20 years. So how do we go about looking at the best electrical solution? Don't worry, I'm not going to scare you by going through every cell of this. I wanted to show you this example of calculation to show you it's not all just PowerPoint engineering we looked at so far. There is some basis in fact behind it. And in fact, although this looks like an Excel spreadsheet, there's details, simulations behind this as well. But you can see it along the columns there. We look at different configurations for a vessel type, and for each of those configurations, we calculate CapEx, we calculate OpEx, we calculate payback time, the emissions, CO2, SOx, NOx, particulates, consumables, fuel and lube oil, EEDI, etc. And from that, we sit down with the owners and designers and try to work out the best solution. But we can't do that on our own, and we have to follow some kind of optimization process. And the most important part of that is the operating profile of the vessel. The first, when we're asked to do some studies in this, the first question we ask back is, what's the vessel operational profile? Now, this can be something as simple as the traditional spreadsheet for the electrical load analysis, showing the power as hotel load and propulsion load for different situations for import, maneuvering, cruising, etc., etc. Something as simple as that. But to be honest, the more complex, the better. So we can take the AAS data from an existing vessel operating on a similar route and use that into our calculations and get an operating profile from that. Or we can take data from sensors on the vessel, either which are already on the vessel or which we can put there for that purpose, to measure power, hotel load, vessel speed over time. From all that, we can plug that into our calculations. We look at the different configurations we saw, whether we're looking at FPP, CPP, diesel mechanical, diesel electric, hybrid, fuel cells, etc. And we come out with an optimized system design, which could look like a simple single line diagram, but it's a lot more than just that, because that doesn't all work together and achieve the results we've calculated without the functionality behind it. So then we would specify the functions required to achieve those results, and that combination then of the system design and the functions is what would give us the superior performance of the vessel going forwards and give us hopefully the flexibility for the vessel. Okay, having said that, I think you've heard enough from me for now. I'll pass back briefly to Torsten to sum up.
Let's conclude, right? So, and of course, we have now enough time for all your questions. Of course, one building block of decarbonization will be electrification. That's it's one of the three, right? And of course, it's quite obvious to consider this now, especially if you're looking at new builds, but of course also for retrofit. There will be, especially whenever it gets to shore connection, but also to zero emission operations in maneuvering in public spaces, right, in harbors, in piers, etc. There will be legislation and local requirements will bump into the next years, right? So all European ports, the big port in this European transport network will get funding to electrify their ports until 2025. So there will be a massive push on shore connection, for instance, in Europe, and it's still happening in China and US, etc. Right? Tony showed you that, of course, if you think twice about your propulsion system for a new build, you can reduce your operating costs and greenhouse gas emissions already today with electrically enhanced or alternative propulsion concept. And on top of that, you gain flexibility for new power sources for different operational profiles. Right? You need to act now. I think there is a threshold on the 2023 EEXI plan that you want to know now how you achieve your EEXI and what can you do on top of that to not have the EEXI impact so big. So for most owners, the question at the moment is, how can I reduce the impact of an engine power limitation to reach my EEXI? that I don't get commercially constrained, especially on the slower vessels like bikers and tankers, and what other optimization options I have, right? And that jump over, of course, is it's already in 18 months, so it's quite soon. Electrical systems and everything we do, it's not about putting a battery on the vessel or putting another switch pod on the vessel. It's the electrical integration which is key, right? Coming from both whatever you do, shore connection, or you do a hybrid upgrade, or you build a new vessel, the integration is the key to optimize your total system. And as I mentioned before, the new means that you need to apply in all cases is what we call an energy management system, which is basically coming on top of the power management system, optimizing your new vessel design, especially if you look at alternative propulsion concepts with hybrid, with different power sources, fuel cells, shore connection, but also a simple PTO, PTI solution that you can optimize much better with an energy management system. That was my summary. So